Hello everyone, and welcome back to this series on single variable calculus, and today we're going to be continuing our exploration of infinite series and discuss several different ways of testing whether a series converges or diverges. So I will anticipate a little bit of comfortability and some basics associated to infinite series in this discussion. But without further ado, let's just jump right into it. So before we, discuss some series of convergence, we need to make sure that we understand what it means to converge. So we're going to be taking a infinite series, S, ranging from 0 to infinity. This lower boundary isn't that important. We can start at 1, 2, 3, or 15. As long as the majority, quote unquote, of that series converges, then the entire series will converge as long as the baby series converges as well. So we say this series converges as long as its partial sum, Sn, which is just a sum from its lower boundary up to some finite number n, converges under some limit value. N goes to infinity. Let's say it's L, and obviously if L is finite, then it's a real number, right? So if the partial sums of the series converges, then we say that the infinite series converges to that number L. And more importantly, if this limit does not converge, and we have several different ways of testing whether limits converge or not, for example, L'Hopital's rule and some of our dominated convergence theorems for limits, then we're going to say that that series S diverges. One of the very first infinite series that people usually encounter is usually called the geometric series, which you may or may not have already investigated. But it's usually represented as an infinite series of the form x to the power of k, where x is some real number. And we have proven in the past that this geometric series does converge to 1 over 1 minus x, provided that x belongs to the open interval minus 1 to 1. And if x is bigger than or equal to 1 or less than or equal to minus 1, then that geometric series diverges. So just as a quick example, if we have the sum from k is equal to 0 to infinity of 1 over 3 to the power of k, since 1 over 3 is in between 0 and 1, that means this is going to converge to 1 over 1 minus 1/3, which is going to be equal to 1 over 2/3, which is going to be equal to 3/2. But if we have the sum from k is equal to 0 to infinity of pi to the power of k, since pi is bigger than or equal to 1, that means this is not going to belong to the set of real numbers, and hence this series diverges, right? So those are some of the basics that we should already be familiar with. So let me introduce the very first theorem that we're going to be using, and this is going to give rise to the very first series convergence test that I want to discuss. And it says the following: if the sum of AK converges, where the sum of AK is an infinite series, where the terms of the infinite series are absolute valued, then the sum of the series without absolute value also converges as well. So this is going to give rise to the very first test, as I already mentioned, known as the absolute convergence test. The absolute convergence test. So let's start off by stating a series. So let's start off very simple. Let's assume that we have the infinite series, the sum from k is equal to 1 to infinity minus 1 to the power of k divided by k cubed. So does this converge or not? Does it converge or not? Well, according to the absolute convergence test, if we consider the sum from k is equal to 1 to infinity of the absolute value of ak, which in this case is the sum from k is equal to 1 to infinity of the absolute value of minus 1 to the power of k over k cubed. Keep in mind that k ranges from 1 to infinity, so k cubed is always going to be positive, so the absolute value is not going to be really changing that much. But the absolute value of minus 1 to the k is always going to be equal to 1. So this is going to be equal to the sum from k is equal to 1 to infinity of 1 divided by k cubed. Now, some of you may already be familiar with this if you've sort of been following along with our series, that this is sometimes referred to a p-series, and all p-series converges provided that that exponent is strictly greater than 1, and 3 is obviously strictly greater than 1, and it in particular converges to this number zeta of 3, which is going to be a real number. right? And zeta 3 is just a special function that represents, some number like the natural log of 5 or the sine of 2.8 or e to the power of pi or something like that. So zeta 3 is just a special number that represents the value for which this series converges to. But aside from that, we have that the sum of the absolute value of the series does converge to a real number. So that means what? So that means that the original series that we had, the sum from k is equal to 1 to infinity of minus 1 to the power of k over k cubed, also converges as well by the absolute convergence test. Now, obviously, this does tell us that it does converges, but one question that you could ask is, what does it converge to? So what does it converge to? So to what does it converge? This is sometimes a very, very complicated question, which we won't get into. There's a pretty much huge computational or recreational mathematics field dedicated to solving these fun integral and infinite series problems, but guaranteed it does converge to something, and we can always approximate that infinite series by just choosing the upper bound to be arbitrarily large, like 5 million, and you can get some decimal accuracy to the value for which it does actually converge to. The absolute convergence test assumes that we know whether or not the absolute value of the sequence converges or not, right? But sometimes we don't know that. So a couple other tests need to be established to sort of cover all grounds. So the alternating series test will reminisce kind of to the absolute convergence test, but it assumes a couple different things. So let's assume that we have some series, S, which ranges from something to infinity, of minus 1 to the power of k times ak. And that k could be k plus 1. You could always factor out a minus 1 to make it a to negative 1 to the power k if you need to. So this series is going to converge if the following conditions are met. First, the limit of the term not associated to the minus 1 to the k, the alternating part, must converge to 0 under a limit. And that series must be eventually decreasing, right? Now keep in mind, just because it's decreasing doesn't necessarily mean it decreases to 0, right? So these conditions 1 and 2 are not necessarily implying one or the other. So what are we going to have for this? Let's actually do a quick example to sort of illustrate. So let's assume that we have the series, the sum from k is equal to 1 to infinity of the cosine of k pi divided by the square root of k. So if we take this particular series and we take the absolute value of cosine of k pi, well, what exactly would that be? So if we look at cosine of 1 pi, that's just going to be equal to minus 1. The cosine of 2 pi, that's going to be equal to positive 1. The cosine of 3 pi, that's going to be equal to minus 1. And you should be able to see that the cosine of k pi will actually be equal to minus 1 to the power of k plus 1. So if we look at this series from a different angle, that's just going to be the sum from k is equal to 1 to infinity of minus 1 to the k plus 1 divided by the square root of k. Now you might be tempted to use the absolute convergence test, take the absolute value, but then you're just going to be left with 1 over the square root of k. And you should know that the square root of k, 1 over, does not converge to zeta of 1/2, because that would be a p series with p less than or equal to 1, and that would diverge. So you cannot use the absolute convergence test here. It would be inconclusive. But we can use the alternating series test to go from here. So this portion, 1 over the square root of k, the thing that does not have the alternating term, is going to be doing what? So ak will be 1 over the square root of k. And what do we know? Well, the limit as k goes to infinity of 1 over the square root of k, that's obviously going to be equal to 0. And we know that 1 over the square root of k is going to be a rational function of some sort with a power of 1/2. So that obviously decays to 0, and it is decreasing, right? So this is converging to 0, and ak is decreasing. So by the alternating series test, so therefore, by the alternating series test, the sum from k is equal to 1 to infinity of the cosine of k pi all over the square root of k converges. Right? So the alternating series test says that this converges, and note that the absolute convergence test is inconclusive for this series, right? Because yeah, it kind of looks like what we can take the absolute value and see if it converges or not, but it's a p series, p less than 1/2. That would imply it diverges, which isn't necessarily true because it has to converge, implying that the original series converges is how the absolute convergence test works. So obviously we see that the alternating series test gives us access to proving that this actual series converges where the absolute convergence test does not, right? But of course, 2 tests is not enough. Let's introduce our third. The next test that I want to mention is called the integral test. So if you're really good at doing integrals, then this is the test for you. So it says the following. So this infinite series, the sum from something to infinity, converges if and only if this integral converges. Also equivalent, this series will diverge if and only if this integral diverges. So the convergence is the same for both this integral and this series. Note that if the integral converges to something, it does not necessarily mean that that series converges to that same exact value either. But it does justify the existence of its limit, even though you might not know what it is. So let's actually look at a quick example. Let's go example 3 with this. Let's do the integral from 0 to infinity of 1 over 1 plus x squared dx. This is a very, famous integral that you might already know. And that's going to be equal to the arctangent. And by the fundamental theorem of calculus for improper integrals, we need to send x to infinity and send x to 0 here. Pi over 2 will be the limit as x goes to infinity for arctangent. That's one of the horizontal asymptotes at positive infinity. And then subtract 0 because arctangent of 0 is 0 because tangent of 0 is equal to 0. That's obviously going to be equal to pi over 2, which is a real number, which means that this integral converges. So since this integral converges, then by the integral test, what series will equivalently converge? So this will be the sum from 0 to infinity. So note the bounds are going to be the same exact thing here. Right? So this series, which is going to be 1 over 1 plus k squared, will also converge. Not necessarily 2 pi over 2, it rarely ever will be the same, but it could be in some special cases. But it definitely converges. Let's actually do one more example. Let's do the sum from 1 to infinity of 1 over x dx. You should know that by the Riemann zeta function or the p-series test, this will diverge, but let's show it in a different way. So this is going to be equal to the natural log of x. And obviously, x needs to range from infinity to 1. That's going to be equal to the natural log of infinity in the limit, and that's going to be natural log of 1, which is going to be equal to the natural log of infinity minus 0, which is going to be the natural log of infinity, which is not a real number. So since this integral diverges, then by the integral test, we have that the sum from k is equal to 1 to infinity of 1 over k also diverges, right? And in case you don't already know, some people refer to this as the harmonic series, right? So the harmonic series diverges, and that's easily provable via the integral test. The fourth series test that I want to discuss is called the series comparison test. And this requires a bit of thinking and strategy to create kind of a bound or an inequality on the series you don't know that converges or not with respect to other series that you know the convergence of. So the series comparison convergence test goes in 2 different directions. So first off, we're going to have the sum of AK and sum of BK both be in series that potentially converge or diverge. The first case is, let's assume that the sum of AK diverges with the sum of AK less than or equal to the sum of BK. So if the sum of AK diverges, that means the sum of AK is an infinite number. There's no way that you're going to put a finite number above an infinite number. So by the same exact logic, you're also going to get that the sum of BK will also diverge. Under similar thinking, let's assume that the sum of bk converges with the sum of bk above it. So if the sum of bk is a finite number, for example 5, there's no way that the sum of ak will be an infinite number, so infinity can't be less than 5. So under this logic, we can see that then the sum of ak must also converge as well. Right, so let's actually do an example of each, one for the convergence and one for the divergence. So the next example, let's do something a little bit more fun. The sum from k is equal to 0 to infinity. Let's do 3 to the power of k all over 4 to the power of k plus 1 plus 5. So what do we have? So we have numbers to powers. Maybe we can compare this to a geometric series, right? So this is, our goal, right? So our goal is to show, is this converges or not, right? But it's similar to a geometric series because it's something to the power of k. So what we can do, notice that if we have a number plus 5 on the bottom, for example, 1 over 1 plus 5 versus 1 over 1, which is smaller, you should be able to see that 1 over 1 plus 5 is less than 1 over 1. But that number here and that number there, as long as they're positive, the logic will still hold. So we can clearly see that this is going to be strictly less than the sum from k is equal to 0 to infinity of 3 to the power of k all over 4 to the power of k plus 1, which is again the same as 4 to the k times 4. So we already know that this is going to be equal to 1 over 4 times the sum from k is equal to 0 to infinity of 3/4 to the power of k. And we know that this is going to be equal to 1/4 times, well, that's from 0 to infinity. 3/4 is between 0 and 1, so it converges by geometric series test. And it's going to converge to 1 over 1 minus 3/4, which is 1 over 1 over 1/4 times 1/4. That's just going to be equal to 1. So we have that our series, the one all the way over here, is less than 1. Therefore, it can't diverge. So that means what? So that means this series, the sum from k is equal to 0 to infinity, 3 to the k all over 4 to the k plus 1 plus 5 converges by the series comparison test. Okay? Let's look at another example. Let's look at this one. Let's do the sum. Let's make this a little bit more fun. Let's do the sum from k is equal to 2 to infinity of k factorial divided by the natural log of k factorial. So take a moment, pause this video, and think about the series. What the k factorial function looks like, natural log of k factorial, what that looks like, and whether the series converges or diverges. What do you think? The first thing I see when I look at this is I have something divided by the natural log of something, where those somethings are the same, obviously. So if I look at, for example, those two graphs, something, in particular y equals something, and the natural log of something, notice that the natural log of something is always less than, strictly, y equals to something. So we can clearly see that x is bigger than the natural log of x. And that's obviously true for all x in the set of real numbers that are strictly greater than 0. So that means what? So that means k factorial must be greater than the natural log of k factorial, because k factorial, where k is a natural number ranging from 2 to infinity, is a real number too. So if I look at these particular things and reciprocate, so if I have 1 over k factorial and 1 over the natural log of k factorial, keep in mind that the inequality will reverse, and we're going to have this particular inequality, which is going to be useful for us, because notice that the natural log of k factorial is on the bottom of our series. So this means what? So this means that the sum from k is equal to 2 to infinity of k factorial over the natural log of k factorial is actually going to be bigger than the sum from k is equal to 2 to infinity of k factorial all over k factorial, which we know is going to be equal to the sum from k is equal to 2 to the infinity of 1, because they're the same, and we know that that's going to be equal to infinity. So we have something is bigger than infinity. Can it be a finite number? Of course not. So we can clearly see that by the series comparison test, the sum from k is equal to 2 to infinity of k factorial all over the natural log of k factorial diverges. right? And that's how you can use the series comparison test for both convergent and divergent series. The fifth convergence test that I want to discuss is called the limit comparison test. This test is going to require us to build or guess a function that we already know the convergence of and compare it in the limit to the function or series that we are currently investigating. So we're going to take two series, the sum of AK and the sum of BK, where one of them converges or diverges and we already know it for whatever reason. And then we're going to define this limit, L, to be the limit as k goes to infinity of the quotient of the two, AK over BK. And the choice of calling AK or BK is up to you, so AK over BK, BK over AK doesn't matter in this regard. So if that limit L is a finite number between 0 and infinity, then the sum of AK converges if and only if the sum of BK converges. Which also means that the sum of AK diverges if and only if the sum of BK also diverges as well. So let's actually look at an example to sort of see how we're going to use this. So let's consider the series, the sum, from k is equal to 1 to infinity of the square root of 5k squared plus 2k plus 1 all over k cubed plus 7. Since it's pretty much a rational function, kind of, usually looking at the leading terms is usually a good place to start for investigating the convergence or divergence of these types of series. So let's start naming our sequences. So AK is going to be our series. So the square root of 5k squared plus 2k plus 1 all over k cubed plus 7. And what we're going to do is we're going to let BK be equal to the square root of 5k squared, so the leading term of the top divided by the leading term of the bottom, which we should be able to see is just the square root of 5 all over k squared, because the square root of k squared is just k, since k is positive, and k divided by k cubed is k squared. So we have this series BK. Now let's investigate its convergence. So if BK is going to be this, then what is its sum? So we're going to do the sum from k is equal to 1 to infinity, same as the limits of the original series. And then we're going to have the square root of 5 over k squared. So that's again going to be our P series. So we already know it converges to the square root of 5 times zeta of 2. And that's obviously going to be a real number. So this series is going to converge. So now what we're going to do is we're going to take the limit of the quotient of these two. So we're going to have the limit as k goes to infinity of AK over BK. And as long as we have a number between 0 and infinity, not inclusive of 0, then this series will also converge. But if it's 0 or an infinite number, it's going to be inconclusive. So let's do the math. So this is going to be equal to what? So the limit as k goes to infinity of our series, the square root of 5k cubed plus 2k plus 1, all over k cubed plus 7, times the reciprocal of bk, so it's going to be k cubed all over the square root of 5k squared. And this is going to be equal to what? So what do we have? So, since we're just looking at rational functions, we can look at the dominant powers, since the limit is k goes to infinity, so we can still use the same calculus 1 tricks, or you can divide top and bottom by k cubed if it makes you feel any better. So this is going to be equal to what? So if I just focus on this term, that's going to be the limit as k goes to infinity of k cubed all over k cubed plus 7, and then times the limit as k goes to infinity of the other term, which is going to be 5k cubed plus 2k plus 1 all over 5k squared. Right? So once we have this, then what else are we going to have in this expression? And that should be 5k cubed. So when we simplify, what do we get? So, oh, and that was k squared, not k cubed. All right, same conclusion if they were both cubed, though. So this is going to be equal to what? So this first limit, this is going to be equal to 1, because 1 divided by 1 is just going to be 1. And then here we're going to have 5k squared over 5k squared. That's also going to be 1, so that's going to be times the square root of 1. And we know that's going to be 1, which is obviously a real number. But moreover, 1 is in between 0 and infinity. This is the requirement that we need for L. right? Therefore, since we have that L is in between 0 and infinity, 0 and positive infinity, then this BK will have the same convergence, as the sum of AK, right? And we already know that this series converges, therefore that series will converge as well, right? So therefore, by the limit comparison test, the sum from k is equal to 1 to infinity of the square root of 5k squared plus 2k plus 1 all over k cubed converges, right? And that's how you use the limit comparison test. But again, it requires you to know the convergence or divergence of some series that you have to build on your own, which can be a little bit more challenging for beginners to build blindly. The next convergence test is actually very nice for beginners because it doesn't have to require to build blind sequences to compare to or know the convergence or divergence of ahead of time. All we have to do is just take our series, which we're going to denote by, again, the sum of AK. We're going to find the AK plus 1th term, or the K plus 1th term of our sequence AK, and just the AK sequence, divide them, take the absolute value, take the limit, and find this limit L. And then we're going to fit it in one of these three boxes. If L is less than 1, and usually greater than or equal to 0, then the sum, or the series, converges absolutely. And if L is bigger than 1, then the series diverges. And if L is equal to 1, it's inconclusive. So you don't have to guess anything. You just have to find a limit. Say if it's bigger than or equal to 1, bigger than, less than, or equal to 1, and then use this test to see what happens. The only downside, if you do hit L is equal to 1, then it's going to be inconclusive, which means you're going to have to use another test to sort of figure out whether the series converges or diverges, right? So that's the downside, I guess, of the ratio test. So again, let's just look at a couple examples to sort of see how it works. So let's look at the sum from k is equal to 1 to infinity of 3 to the power of k all over k factorial. So our sequence is going to be that term there. So AK will be equal to 3 to the k all over k factorial, which means that AK plus 1 will be equal to 3 to the k plus 1 all over k plus 1 factorial, which we can, of course, re-represent as 3 to the k times 3 all over k plus 1 times k factorial. So what is this limit going to be? So the limit will be equal to the limit as k goes to infinity of the absolute value of AK plus 1, which is going to be 3 to the k times 3 all over k plus 1 times k factorial divided by AK, or multiplied by the reciprocal, so that's going to be k factorial all over 3 to the power of k. And then let's simplify to see what happens. So we have a 3k top and bottom, k factorial top and bottom, and then we're just going to be left with the limit as k goes to infinity of, what do we have here? So we're going to have 3 all over k plus 1, and that's always going to be positive, but so we don't need the absolute value, and that's going to be 0, which is less than 1. Right? So we have a number for L that is less than 1, therefore what? So that means the sum from k is equal to 1 to infinity of 3 to the k all over k factorial converges absolutely by the ratio test. All right, so it's actually quite nice. Let's look at another example just to make sure we have it. So example number 9. So let's assume that our sequence AK is now k squared all over k squared plus 4k plus 1. You can use another test to test whether this converges or diverges, but I sort of want to show how the ratio test works with it. So what would AK plus 1 be? So AK plus 1 will be equal to k plus 1 squared, k plus 1 squared plus 4k plus 1, and then that's going to simplify. So k squared plus 2k plus 1 all over k squared plus 6k plus 6 once you simplify and combine like terms. So let's take the limit as k goes to infinity for L. So L will be equal to the limit as k goes to infinity of the absolute value of ak plus 1, so k squared plus 2k plus 1, all over k squared plus 6k plus 6 times the reciprocal of ak, so that's going to be k squared plus 4k plus 1, all over k squared. And then we can just take the leading terms once you distribute. So we have k squared times k squared, that's k to the 4. We have k squared times k squared, that's going to be k to the 4. So this is going to be equal to the limit as k goes to infinity of the absolute value of k to the power of 4 plus some stuff, all over k to the 4 plus some stuff. So by the dominated convergence test, those leading terms are all we really care about. So that's going to be equal to the limit as k goes to infinity of k to the 4 all over k to the 4, which we know is going to be equal to 1. So by the ratio test, we have a limit L is equal to 1, so that's inconclusive. So that means the convergence of the sum from k is equal to 0 to infinity of k squared all over k squared plus 4k plus 1 is inconclusive by the ratio test, right? So that means you need to use another test in order to establish its convergence, but I leave to you to figure out which test that we have already mentioned is more appropriate for this particular series. The seventh and last series convergence test that I wanted to describe today is known as the root test, and this test reminisces very strongly with the ratio test, except it uses a different L. So again, let's assume that we have some infinite series, the sum of ak, and define L to be the limit as k goes to infinity of the kth root of the absolute value of our sequence. The rest follows the same as our ratio test. If L is less than 1, then the series converges absolutely. If L is bigger than 1, then the series diverges. And our sad case, if L is equal to 1, then the ratio test is inconclusive. So let's look at a quick example to sort of see how this is going to be used. So usually you have to be very, very good with powers, and sometimes you can be super clever with logarithms and exponentials using the root test. So those are just some little things to keep in the back of your mind. So let's do the sum from k is equal to 1 to infinity of 2 to the power of minus k squared on the exponent. And then let's assume that we have the arctangent of k all raised to the power of k in the denominator, right? So it's very important to note that this is always positive, right? This is going to be our AK. So the absolute value isn't really going to be much of a problem for us. So let's look at our special L. So this is going to be the limit as k goes to infinity of the kth root of the absolute value of AK. So what is this going to be? So you might want to pause the video just to see if you can do the algebra for this. So this is going to be equal to the limit as k goes to infinity of the kth root. So the kth root of this very complicated looking sequence, 2 to the minus k squared, and then arctangent of k raised to the power of k. Now keep in mind, kth root is the same as to the power of 1 over k. So I can write this as the limit as k goes to infinity of 2 to the minus k squared to the power of 1 over k, and then the arctangent of k to the power of k, all to the power of 1 over k. So lots of parentheses there, but most importantly, notice that that k and that 1 over k will cancel, just leaving us with arctangent in the bottom. And on the top, we're going to have minus k squared divided by k, which is just going to be equal to minus k once we simplify that expression, because we have minus k squared all over k, which is going to just be minus k. So this actually simplifies quite nicely. This is going to be the limit as k goes to infinity of 2 to the power of minus k all over the arctangent of k. So our very complicated sequence actually looks very nice. And what do we have here? So 2 to the minus k goes to 0 as k goes to infinity, and arctangent of k goes to pi over 2 as k goes to infinity, and 0 divided by a finite number is obviously 0, and 0 is less than 1. This is what we need for our value of L, right? So therefore, since L is less than 1, that means the sum from k is equal to 1 to infinity of 2 to the power of minus k squared all over the arctangent of k to the power of k converges by the root test. Converges to what? Obviously a different story, but that's how we can use the root test. So I hope this was able to give you sort of a brief overview of 7 of the most common convergence tests that are used to establish the convergence or divergence of infinite series. Obviously the hardest part is figuring out when to use each one by looking at a random series, but that just comes with practice. So I hope you enjoyed this video, and I'll see you in the next one. Take care.